I'm going to talk about word maps on groups. This is something that I have been interested in from my PhD time, and this is something that has been a very active theme, and very enormous progress has been seen in this direction for the last couple of decades. So there are multiple point of views from which this can be introduced, but I chose one of them, which is something easier to state and nice. So let me start with what is wording problem in number theory. Okay, so this starts with Lagrange 4-square theorem, which was in 1770. So every positive integer can be written as a sum of at most 4 squares. Right? So everything can be written as a sum of 4 squares, and 4 is the best possible in the sense that if you see 4, if you see the number 7 and you want to write it in the sum of 4 squares, then just 2 square plus 1 square plus 1 square plus 1 square. So you need 4. You cannot do it with less number of things, right? So 4 is the best possible. And in the same year, wording actually asked the following generalization of this problem, that why do you want to write it in sum of squares, but you can do it with sum of kth powers, right? For an arbitrary natural number k. So given a natural number k, does there exist a number gk such that every positive integer can be represented as a sum of at most gk kth powers of positive integers, right? So and minimum here I write in bracket, because if there exists such a number, then we can always choose something that is minimum, right? So this is something that wording asked, and this was proved in a celebrated paper of Hilbert in 1909, solving this wording problem in affirmative, which is now called the Hilbert wording problem. So yeah, so for example, Lagrange result shows that G2 is equal to 4. Right? So 4 squares, right? So several mathematicians have contributed towards finding the exact value of gk. For example, G3 is 9, which simply means that every positive integer can be written as a sum of 9 cubes, at most 9 cubes, and 9 is the best possible for that matter. G4 is 19, and so on, and a general formula to determine gk is now known. Okay, so this motivated many mathematicians to generalize this sort of an idea to different mathematical structures, like for example groups, and non-commutative structure like groups, and algebras, matrix algebras, and so on and so forth, right? So in groups we do not have so we have only one operation, right? The product, let's say, for example. So so we cannot talk about sum of squares or something like that. We have to talk about product of powers, right? So here is a theorem, a Hilbert wording analog for finite simple groups. Okay, so what are finite simple groups? So a group is called simple if it has no non-trivial normal subgroup. Okay, and roughly speaking, these in the realm of finite groups, these are very important groups, because very roughly speaking, they are somewhat the analog of prime numbers in the realm of integers, right? But of course, the relation is not so strong as in number theory, but yeah. So examples of these simple groups are alternating groups, n greater or equal to 5. These are the group of subgroup of all even permutations in the bigger symmetric group Sn. And for n greater or equal to 5, projective special linear group over finite fields, because PSL and Q. So you take determinant n cross n determinant 1 matrices with entries in the finite field FQ, and you quotient out by the center. That is what is the PSL and QA, and etc. So this second example falls under the broad family of simple groups called the finite simple groups of Lie type. Okay, because if I replace this Q by complex numbers or reals, then these are Lie groups. Okay, so so here is an analog of this Hilbert wording problem for number theory. So this was done by Saxel and Wilson in 1996. So given a positive integer k, there is a number fk such that if g is a finite simple group of exponent not dividing k, then every element of g is a product of fk kth powers of g. Okay, so so what is meant by an exponent of a group? So it's the minimum number such that every element of that group raised to that power gives you identity. Okay, so you see that this is a trivial exclusion, because if my power divides the exponent, then any if I raise it to the power k, then I get identity, and then I take subsequent products, I get identity only, I get nothing more, right? So what does it say? So it says that, so choose any k, right, and then you look at any finite simple group for that matter, and every element in G can be written as a product of kth powers, fk many kth powers in that group G, right? So in the number theoretic setting, we are in the set of natural numbers or integers. Now we are in this group setting, right? And yeah, so and this is a direct analog of Lagrange theorem. So this is by Liebeck, O'Brien, Shalev, TF 2012. That so you see that, but this says that fk. So what is fk, right? So this is for k equals to 2. These mathematicians prove that every element of a finite simple group is a product of 2 squares of G. So there it was a sum of 4 squares. Now it's a product of 2 squares, right? So that is, given G in G, there exist A and B in G such that G is equal to A squared B squared, right? Okay, so yeah, so now these results can be put under a general umbrella called the idea of word maps on groups. So let me define what these are, and then I'll show you how these fall under that situation. So what we do is the following. So we take a non-trivial word in D generators. So it's an element of the free group with D generators. So all we can do is, you can think of it like monomials, like so x1 to the alpha 1, x2 to the alpha 2, and so on. But note that we can have negative exponents, negative powers, and this is non-commutative. So for example, if I like x1 square, x2 is not same as x1, x2, x1. Okay, so keep that in mind, and then we have the following obvious map induced by this word map. So I start with a group G, okay, and then what we do is just evaluate this tuple G1, G2, GD. So GD is simply the Cartesian product of G, the many copies of G, and then I simply evaluate this on this tuple G1, G2, GD in W of G1, G2, GD. So let's see some examples to get this clear. So let us take the free group in one generator. So it's just powers of a letter X, right? And then what we get is this induced word map is just the power map from G to G given by G maps to G to the R, right? Similarly, we have this commutator word, which is basically xy, x inverse, y inverse on the free group F2 with 2 letters, and then this induces this following map from G cross G to G, saying taking this pair GH evaluated on this GH, G inverse, H inverse, right? So what does, therefore, if we go back here, what does it say? It says that if I am so there is a number fk such that if I take variables x1, x2 dot xfk, then the word x1 to the k, x2 to the k dot xfk to the k, this word, when you evaluate on any finite simple group, this map is basically surjective. The induced word map is surjective. Okay, so every element can be written in that fashion, right? And in particular, therefore, it says that if you have this word x square, y square in the free group with 2 generators, then the induced word map is basically surjective on all finite simple groups. Okay, so this is what it says, and yeah, the general question is to study the properties of image of such maps on a group or a class of groups. For example, in this case, we have a huge class of groups called the finite simple groups, and there is a very beautiful survey article I would suggest here, some results and problems in the theory of word maps by Shalev in 2013, which have many different perspectives of this problem and many results and different directions. So I am going to finish my talk with the following thing. Because I gave an example of this commutator word xy, x inverse, y inverse, so I must talk about this Ore conjecture. So this Ore Austin Ore in 1950 showed that every element of the alternating group n greater equal to 5 is a commutator. So that is, this word map xy, x inverse, y inverse is surjective on an. Okay, and at that time the classification of finite simple groups were not known, and he could not proceed to give some general result over all finite simple groups. Note that this is a finite simple group, but he conjectured that it is true for all finite simple groups. And this long-standing conjecture was finally settled in the affirmative by the works of Ehlers and Gurdjieff in 1998 and Liebeck, O'Brien, Charles-Leventieff in 2010. So this map, therefore, going back here, is also surjective on all finite simple groups. Okay, so once again, this beautiful article by Gunter Male, Proof of Orr's Conjecture, talks about this journey and talks about different methods which are not only used for this, but are useful in general. So with this I will finish my talk.
Thank you for this lovely talk.